Hard?
Yeah, it was pretty hard.
You had to get 20 points out of, I think 44 was the total. Maybe it was 40.
I think I got maybe like 10 points, 8 points.
Ooh, okay. We'll have to look at them and see then. Okay. Well, it's the first test on your first. Oh, iffy. That's not so bad. Iffy could go either way. First test in your first course. We'll see. First quiz in your first physics course. All right. So the things that are coming up, we're ahead of schedule in lecture, but the things that are coming up are your chapter 3 homework mastering physics and your chapter 3 PIP. And that's due tonight. So why don't we spend whatever time we spend together after the test answering questions on problems. Who has a question?
Actually, I had a question for the lab due on Wednesday. So I know you want the graph, but did you also want us to submit the data too and our like work on the data?
Yeah, there's a section in the lab report for data, in which case you'll have a data table that looks something like this. If I remember correctly, you would probably have acceleration. You'd probably have V, then acceleration, then the sine of theta or theta, however you choose to do it, and give me a table of those values. And then the graph actually goes in your results section. Does that answer your question?
Yeah, thank you.
Okay.
Hey, Professor?
Yes.
Can I ask you a question from the quiz? No one has a question?
Maybe. Hold on.
Okay.
Yeah, hold on a second. Adam, there's a note for you in the chat. Would you take a second to look at it? Thanks, Adam. Okay, so what question on the test did you want to ask about, Jonathan?
Well, there's actually like two, but for number 10, I was like, if I'm not going to get points, I might as well not get big points. And so I tried to go for it. And I got kind of close, I think, but the issue I was having is like, I felt like there should have been a height on where the cannon was shot from.
Oh, let me look at it.
Yeah, I was a little bit confused.
Oh, no, you don't need to have a height from where the cannon was shot from, for the simple reason that it's shot from the origin. And you're looking for how far down the slope it lands, but the slope goes down to infinity. It'll go as far as needed so that you know, it continues until the cannonball lands there. So it looks something like this. Right?
Mm-hmm.
And V0, oh, was at 10 degrees. Oh, 30 degrees, I'm sorry.
The
30
slope was 10.
degrees, 10 degrees. And this is V0. So you play the trick that we learned in class and orient your axes so that the x-axis aligns with the slope. Of course, it doesn't have to be the x; it could be whatever axis. There you go. Okay, so this is the x-axis and this is the y-axis. See, now in this problem, you want to know what's the x value where it lands. And you begin right here at the origin. So you don't need to know a height.
If I'm just like trying to ask, like, I'm just trying to like make it make sense to me. And like, I'm still trying to grasp it and understand that. Like what I was doing is like, I try to take it, but then I was thinking like, oh, like I would have to find, I'd have to find like the tangent of like a fit. I don't know. I think like I'm just in my head. Okay.
Well, okay, well, let's at least set it up. Here's G, and A in the Y direction is minus G cosine theta, and A in the X direction is G sine theta. So you have your two kinematic equations. X equals V0x, which is actually, this is a tricky part, V0 cosine 40 degrees, right? Because it's the sum of these two with respect to x, plus 1/2 G sine theta is 10 degrees times t squared, and y is equal to V0 sine 40 degrees minus 1/2 G cosine theta, where theta again is 10 degrees, t squared. And I made a mistake here. I forgot to multiply by t, obviously. Okay, so you want the value of x when y is equal to 0. Well, if y is equal to 0, that occurs at two points. T V0 sine 40 degrees so t equals 0 is a solution, but that's obviously true. Y does equal 0 at t equals 0. So solve this for t, and then simply plug that value of t right there.
Okay. Is it
The tricky part is to see that this angle here is 40 degrees. So it's cosine and sine of 40 here.
okay? I'm just trying to like trying to figure it out. And like my question, so I did, yeah, the velocity at x, I did 40 cosine 30, which like obviously is wrong. And then at the y, I did at sine of 30 times
Okay.
40 to get 20. But then I was thinking that at that point, I feel like you need to take like the tangent of 10 degrees, like basically like wherever it lands, it's basically going to make a square. And I was trying to find basically right under the cannon to wherever it would correlate to on the slope. Does that make sense?
Okay, sounds like your only mistake was putting in 30 instead of 40 here.
Okay, but if we had how high the cannon was, that would work, right?
Well, but measured from where? I mean, if I give you a 0 point.
Like, from where it lands, I guess. Okay.
But
okay, I
you
get
don't know where
it.
it lands until you solve the problem. If I told you that the height here, let's say it landed right there, and I told you that this height, well, then you can use trigonometry to figure out how far down the slope it lands. You
I
don't
think
have
that's what I was
do
trying to do.
mathematics.
Okay.
Yeah. What about V when it lands?
I didn't even get the first part, so I didn't even try.
Well, the second part is what is the speed when it lands? I think I said speed. So V sub S is equal to V0 cosine 40 degrees plus A sub X T, and Vy is equal to V0 sine 40 degrees plus A sub Y T. Well, A sub X and Y you know. And you know the time because you solve the time right here. So at that time, the X component is something, and the Y component is something. And then the speed is just this. That's the definition of speed, right? Magnitude of the velocity.
Just out of curiosity, sorry, I'm going to take a little time. Everybody else has questions, please interrupt. How it's like when it's the impact, obviously it makes like a stop at one point when the velocity is zero, and then like the force is pushed back against it. Like do we figure that out? Like if I throw a ball on the floor, like at a certain point the velocity is going to be zero because it hits the floor before it starts to bounce back, it would be zero.
Okay. It'll be the speed will be zero in an instant. Assuming the ball is perfectly rigid. The speed will be zero at an instant. And that's not really what I meant. What I meant was the speed just before it hits the ground.
Okay.
In fact, that's what we'll always do.
No, I was just curious.
Yeah, okay. All right. Okay, other question on anything?
Can you work out the problem on the problem J5?
Yeah, 3 again, right?
Yes.
Okay. So plane can fly at 150 meters per second with the air, and the wind is to the southwest at speed equals 50 meters per second. In what direction should the plane head or fly directly north? Okay. Well, this is kind of a problem similar to the relative speed problem, but it's given to you in a little bit different form. So let's say this is north. Okay. Now, what do we know? We know that the wind is from the southwest at 50 meters per second. So that means V of the wind is this. So this is V of the wind, and this is 45 degrees. So from the southwest means this way. Now you know that the plane can fly at a speed of 150 meters per second with respect to the air. So this represents the speed of the airplane, or the velocity of the airplane, and it is 150, and this angle we do not know. So if the wind is pushing him in the direction of the wind, he's got to actually steer in this direction in order to fly due north. But we need to know what that angle theta is. Okay, so what do we need? We need, for it to fly directly north, we need the horizontal component of the wind to exactly cancel out the horizontal component of the velocity of the airplane. So that means we need V of the wind, which I think was 50, right? V of the wind times the cosine of 45 degrees has to equal V of the airplane times the sine of theta, where I've defined theta as this angle right here. And that's what I think what the problem is asking for, is for that value of theta. So you know everything here, solve for theta. Now the other part is, what will be its ground speed? Both of these velocities, the velocity of the wind and the velocity of the airplane, are with respect to the ground. So the plane speed with respect to the ground is just going to be VA in the northerly direction plus VW in the northerly direction. So the ground speed is just going to be VA cosine theta, but you already know what theta is from the first part, plus VW sine of 45 degrees. Okay, does that help you?
Yeah, I just like forgot where the formula comes from. That was like more where I was getting confused.
Which formula do you mean?
The V cosine 45 equals V sine theta.
Okay, well that comes from the fact that the component here of VA horizontally has to cancel the component of VW horizontally in order for the net to be in the north direction. And once you know that the plane is going in the northerly direction, then you can figure out what that speed is, because it's just going to be just like the motorcyclist on the flat car, on the railroad car. The wind is going north at so many meters per second. He's going north at so many meters per second. Add them up, that'll be the ground speed. I may have said something not quite right. This VW is with respect to the ground. This VA is with respect to the air, but the air is moving. So the northern component of VA plus the north component of VW gives you the ground speed. Okay? Yes.
Like this is more just to understand it. Like, and I get it. I'm just kind of curious. If you want to, could you kind of like cheat the system to make both of the vectors like 50? Like, could you somehow divide the plane speed by 3? Like, just to get the numbers the same? Because I feel like that would take out the speed component. Does that make sense?
If I make VA 50, then this angle here has to be 45 degrees because its component horizontally has to cancel out the component of VW. But if I do that, my ground speed in the northerly direction will be much less.
I was just curious if like you could somehow like cancel out one of the like if you cancel like the speed component, but I didn't think so. I was just kind of curious.
Okay, I'm not quite sure what you mean.
I was just trying to take out a variable, but I think you're right. I don't think there's any way that you could even do that.
Oh, Aurelio says, what if we just add these two together? Well, we can, but the issue is we don't know theta. So we need a condition in order to determine what theta is. And the condition is that the net speed has to only be, or net velocity, has to only be in the northerly direction. That's what tells you what theta is. So if you don't know what theta is, yes, if you added these two component-wise, you would get the final speed. In fact, let's just do it that way. So theta is a parameter. We're trying to figure out what it is. We know that V with respect to the ground is going to be in the x direction, VW cosine 45 degrees minus VA sine theta, that's in the I direction, plus VW sine 45 degrees plus V of the airplane cosine theta in the J direction. That's exactly what we did. But we used the condition that this must equal 0 because we want the plane to fly directly north. And that's what tells us what the value of theta is. Then if we plug in that value of theta, of course, we get 0 here. And this is the ground speed in the positive y direction, which is north. Okay? It will always be true, Jonathan, that V ground speed equals VW plus VA because A is with respect to W. So that's just the two-dimensional version of the one-dimensional formula that we derived from the standard configuration. And so you're absolutely right to do this. Add them together. Now apply your condition. That piece has to equal 0. All right, are there any others? There's no other questions at all?
I was actually wondering if we could go over M3 on the PIP.
So chapter 3, M3. So a bird is initially flying horizontally east at 21.1 meters per second, but 1 second later, it has changed direction so that it is flying horizontally 7 degrees north of east at the same speed. What are the magnitude and direction of the acceleration vector during that 1 second time interval? Well, what they're really asking you for is the average acceleration vector. And let's draw ourselves a picture. They should pay me a nickel for every time I say, let's draw a picture. I would get paid more than I'm being paid. Okay. So my V1 vector is like this. Directly east, right? And it's 21.1 meters per second. And 1 second later, it has a new velocity vector, which is this. And that new velocity vector has the same magnitude, 21.1, but it's at an angle of 7 degrees to the north of east. Did I interpret that correctly? To the north of east. North of east. So north east. So let's call this the positive x direction. Let's call this the positive y direction. Now, what is the definition of the average acceleration? It's delta v over delta t. Delta t is 1 second. It's a scalar. We divide by 1. But what is delta v? Where delta v is v2 minus v1. And this is v1, and this is v2. So the average acceleration is 1 over delta t. Delta t is just 1 second. And what is v2? Well, v2 is 21.1 cosine 7 degrees in the I direction plus 21.1 times the sine of 7 degrees in the j direction. Now I want to subtract v1. Well, v1 is minus 21.1 in the I direction. Okay. And well, let's just work out the numbers. So that equals so this is minus 0.157 in the I direction plus 2.57j. That's the acceleration vector. Now we want to know the angle of the acceleration vector. Well, what is the acceleration vector? It's v2 minus v1 So here is V2, only we want it to be negative, don't we? So that's like this. And our acceleration vector should be in that direction. Oh, only I did V1 minus V2 instead of V2 minus V1. Okay, so obviously it just goes the other way.
Wait, Professor, can you explain why you subtracted 21.1i again?
Well, it's V2 minus V1. So V2 is this vector, and V1 is that vector. So this is the I component, add the two components, and then this is the J component. Was that your question?
Yes, that was my question.
Okay. So now let's look at where we expect it to be. Well, V2 minus V1 goes like that. And the acceleration is going to be that way. So we'd better get a value for theta here. So this is my value of theta. We'd better get a value of theta in the second quadrant. So let's make sure that we do. So I want theta equals the arc tangent of 2.57 divided by minus 0.157. Well, that's definitely going to be in the second quadrant. So let's work out what that number is. So I get minus 86.5 degrees, but what do I have to do to fix this?
You have to add 180.
I have to add 180. And I get 93.5 degrees. So there's this angle right here is only 3.5 degrees. So 3.5 degrees west of north is my acceleration vector, my direction of my acceleration vector. Okay, does anybody have any questions on this one still? Okay. Other questions?
I had one for mastering physics. Problem, I think it's problem 4, part B.
Okay, what's the actual number of the problem?
3.47.
Okay. Ah, okay, good. So a test rock. Sorry?
I got the first part, like I kind of understood the first part, so like the maximum
Good.
height. I just need help on the, I'm like kind of lost in what to do for like the horizontal range.
Oh, okay. Well, let's okay, this is 35 degrees, and this here is 200 meters. All right, so what's it doing? It's accelerating along a 200-meter incline at 1.9 meters per second squared. And the instant the rocket leaves it, the engines turn off and the rocket is ballistic. So basically, our V0 is that. And the easiest way to, well, let's see. The easiest way to do this is to make a new coordinate system such that the origin is right where the engines turn off. So it leaves the end of the incline at the origin. And this angle here is 35 degrees. Okay, so what is this distance right here? Well, this distance h equals what? 200 meters times the tangent of 35 degrees. Is that right?
Yeah.
No, not tangent, sine.
It's a sign.
It's a sine. Ah! Yes, okay. So we know that distance. So we'll write down the equation for the path. Y equals x tangent theta, theta is 35 degrees, minus gx squared over 2 v0 squared cosine squared theta. So if we knew v0, we could put in h as the value of y and solve for x. And you're going to get a negative and a positive solution for x. You obviously are going to pick the positive one. Okay. So what is v0? Well, along this ramp here, we have that the distance along the ramp, we got to give it a new variable. Let's call it d. The distance along the ramp is equal to 1/2 a t squared, only that's not going to help. So we want a different kinematic equation. What we want is this v0 here squared minus the starting speed here, which is 0. That's supposed to be a 0 squared, is equal to 2a times 200 meters. So that gives us v0. Now, that's part A, right? Oh, part A is the range. No, part B is the range. Part A is the maximum height above the ground. Okay. Well, let's go back to our kinematic equations. And the path of this thing is going to look something like this, right? And the maximum height is going to be right here. Let's call that capital H. Well, let's see. V in the y direction is equal to V0 sine 35 degrees minus GT. So right there at its maximum height, its y component of velocity is 0. Now solve for t. Now I know that y is equal to v0 in the y direction, t minus 1/2 gt squared. So plug in the t from this solution here, and that will give you y, but that actually is this height right here. You have to add to that this height to get the maximum above the ground. But you already said you did part A without any problem.
Yeah, I just needed help on the range one.
Okay, so use the equation of the path and it makes it simple.
Okay, yeah, I kind of get it.
Okay, this isn't an x, this is crossing out the y. So h is equal to this. Okay, good. Other questions? Okay, let's see if there's anything in the chat. Someone is asking for the last one from chapter 3. So that's 3.76, right? Oh, okay. Oh. Okay. All right. So we've got a graph we're given that looks something like this. Here's the distance d, and here is the launch angle theta, and you've got some data points here that they give you. So a spring gun shoots a rock from the ground with a speed v0 at an angle theta naught above the ground. You've been asked to determine v0 from the way the spring gun is constructed. You know that to a good approximation, v0 is independent of the launch angle. So v0 is a constant. And it's the launch angle and the range that is changing. Okay. So part A, they ask you to select a way to represent the data well as a straight line. All right, so what is the distance as a function? What is the range as a function of the launch angle? So this actually shouldn't be a D, this should be an R using our terminology. Well, what is our formula for the range? The range is equal to V0 squared divided by G times the sine of 2 theta. Isn't that right? So let's graph R versus the sine of 2 theta. and we should get a straight line. So you can read off these data points what the value of R is and what the value of theta is, and plot those points in Excel. And this slope is therefore equal to V0 squared over G, and from that you can determine V0. So is that what they're actually asking you to do? Yes. Use the slope of the best straight line set to calculate V0. And when the launch angle is 36.9 degrees, what maximum height above the ground does the rock reach? Well, you know V0, and we just figured out how to do the maximum height, right? Vy is equal to 0, but that's equal to V0 times the sine of the launch angle theta, and they gave it to you as 36.9 degrees, minus GT. And y is equal to V0 sine theta t minus 1/2 GT squared. So use this formula to solve for the time and plug it in to get the height. Is that good? Does that answer your question? Okay, good. All right, does anyone else have a question? Okay. All right. Ah, you're back, Adam. Did you have any questions on Chapter 3 PIP or Mastering Physics, Adam? Okay. Well then, if nobody else has any questions, I'll let you go. You've got 45 minutes of class period. So work on Mastering Physics and PIP during those 45 minutes. And that's due tonight. Okay. Anybody have anything they want to say? All right. Well, then I hope you all have a really good night, and I will see you on Wednesday. Oh, let me look at the schedule though and make sure that of what we're doing. Okay, we're just having lecture on Wednesday. We'll start chapter 4. Okay, everybody have a good evening.
Thank you, Professor.
Okay, goodbye.
Thank you.
I have a question about the lab from last week.
Sure, Adam.
What are we submitting, the data and the graphs, or?
Yes, you're going to write a report, and that report is going to follow the model that's given in the lab manual.
Okay.
Oh, Professor, the
Yes.
lab manual model, you're saying that's in the back of, let me pull it up real quick. You're saying it's in the back of the, I don't remember, it's like a 50-page, yeah, the lab manual. Let me pull it up real quick. I didn't see one, and I don't know if like I'm just not paying enough attention or what.
Let's look at it and make sure it's there, but I really thought it was there.
Because all I saw was like a description telling you like what to do. Let's see. Yeah, I think it's page 48. Yeah, I see format of a lab write-up.